Welcome to Review Lecture 4.4, Power and DC Circuits. After this, you should be able to calculate the power dissipated in resistances, calculate the cost of electric power. Now, power and electric circuits. In the figure, we see a circuit consisting of a battery, B, that is connected by wires, which we will assume to have negligible resistance, to an unspecified conducting device. The battery maintains a potential difference of magnitude V across its own terminals, and thus, because of the wires, across the terminals of the unspecified device. The greater potential is at terminal A of the device than at terminal B because A is connected to the positive side of the battery. Power P, or rate of energy transfer in an electrical device across which a potential difference V is maintained, as power equals I times V, where I is the current and V is the potential. The units on that is a watt equals 1 amp volt, also equals 1 joule per second. It's a watt we had before. If the device is a resistor, the power can also be written as power equals I squared R, or V squared over R. This part here is called the I squared R loss, or I squared R law, and energy losses due to resistance in wires are called the I squared R losses. Warning, this only applies to DC or DC with pure resistances. It gets much more complicated when we deal with AC, which we'll talk about later. How can you express electric power in terms of current and voltage? Electric power is equal to the product of current and voltage, so P equals IV. Okay, given a length of uniform heating wire made of a nickel, chromium, iron alloy called nichrome, has a resistance of R of 72 ohms. At what rate is energy dissipated in each of the following situations? Number one, a potential difference of 120 volts is applied across the full length of the wire. Number two, the wire is cut in half, and a potential difference of 120 volts is applied across each length of each half. In other words, the two halves are connected in parallel with each other. Okay, so then we know the voltage is 120 volts. R1, which is the original wire, is 72 ohms. L2, which will be the new wire, is 1/2 of L1. We need to know P. And we also know, because they're going to be working in parallel, two wires are going to dissipate twice the energy as one wire will. The physics of this is power dissipation and the resistance. The formula is P equals V squared over R, and R equals rho L over A. For part one, P is just the 120 volts squared divided by the 72 ohms, or 200 watts. For part two, R2 equals rho L2 over A2, and because the only thing is changing here is we're cutting the length in half, so it'll be 1/2 of R1. That ends up being 36 ohms. Two wires are going to dissipate 2 times the power as one wire, because they'll both be running at the same time. So P2 equals 2 times 120 volts squared divided by 36 ohms, or 800 watts, so 4 times as much power. At 11 cents a kilowatt hour, which is $0.110 per kilowatt hours, what does it cost to leave a 40-watt porch light on 24 hours a day for a year? The knowns in this are time equals 1 year, cost per kilowatt hour is $0.110 per kilowatt hour. The power is 40 watts, what's the cost? Physics of this, power dissipated in a resistance. The power company actually charges you for energy. Kilowatt hours is a unit of energy, and energy equals power times time. No, you can't forget the past or anything you learned in Physics 1. The solution of this is the cost equals the power times the time times the cost per kilowatt hour. So it's 0.040 kilowatts, that's the 40 watts converted to kilowatts, times $0.11 per kilowatt hour, times 24 hours per day, times 365 days per year, times 1 year. If you check the units, they cancel out correctly and they leave you with dollars. Cost is $38.54. Now, this is pretty high. I would invest in either an inexpensive photocell device that will automatically turn off the light during the day. Payback time on that might be about, depending on the cost of this device and how fancy you want it to get, 1 or 2 years. But even better than that would be to get an LED bulb. A 40-watt equivalent LED bulb uses about 5 watts and would last for years. This would probably save you about half of this. This is going to save you 3/4. A power station delivers 520 kilowatts of power to a factory through wires with total resistance of 3 ohms. How much less power is wasted in the wires if the electricity is delivered at 50 kilovolts rather than 12 kilovolts? Okay, the resistance of the wires is 3 ohms. The power is 520 kilowatts. V1 is 12 kilovolts and V2 is 50 kilovolts. The physics of this is power dissipated through resistance. The formula P equals IV equals I squared R. I equals P over V, and that will be the delivered current. The solution, P loss is I squared R, or P over V quantity squared times R. Case 1, V1 is 12 kilowatts. So the loss in first case is 520 kilowatts divided by the 12 kilovolts. That total is squared. So the 520 divided by 12 is squared. Anyway, it's 3 ohms, which is resistance, and a bunch of units conversions here, including one for kilovolts to volts. When we do that, we wind up with 5.63 kilowatts. Case 2, V2 is 50 kilovolts. 520 kilowatts divided by the 50 kilovolts, that whole thing squared, times the 3 ohms for the resistance, times a bunch of units conversion. It ends up being 0.324 kilowatts. The difference is 5.31 kilowatts. This problem demonstrates why we have those high voltage, high tension lines for a long distance power transmission. The power is the current times the voltage. So the higher the voltage, the lower the current. And since the power loss is I squared R, you want to keep that current as low as possible. A small immersion heater can be used in a car to heat a cup of water for coffee. If the heater can heat 150 milliliters of water from 5 degrees C to 95 degrees C in 5 minutes, approximately how much current does it draw from the 12-volt battery, and what is the resistance? Assume the efficiency is 60%. Okay, we know the volume of the water is 150 milliliters. The time is 300 seconds. That's just the 5 minutes converted to seconds. Delta T, which is the temperature rise, is 90 degrees C. That's just from this. The voltage is 12 volts. The efficiency is 60%. And the density of water is 1 gram per milliliter. And the specific heat for water is 4.186 joules per gram degree C. Of course, you can look that up. The physics of this is the power used by resistance, the energy required to heat water, energy law, and Ohm's law. Formula is Q equals MC delta T. Mass is also the density times the volume. The power is the current times the voltage. It also equals the energy divided by time, and resistance is V over I. We energy law, energy in equals energy output plus energy loss. Our energy equals IVT equals Q plus E loss. Q is, of course, the water, the heat needed to heat the water. The efficiency then is N, and that's what you want divided by what you pay for. That's what efficiency always is. And that, in this case, is what you want is the heating of the water. So that's the Q. And what you pay for is the energy that you're sending from the battery, you're getting from the battery. So then Q is MC delta T and E is just IVT. So this becomes the efficiency N is MC delta T divided by IVT. And that equals 0.60 written as a fraction. So then we solve this for I. I will be the density times the volume times the specific heat times the temperature rise divided by the efficiency times the voltage times time. Plug in the numbers. The current is, this is the volume, 150 milliliters. This is density, 1 gram per milliliter. The specific heat is 4.186 joules per gram degree C. Delta T is 90 degrees C. This is unit conversion, 1 volt amp seconds per 1 joule. The efficiency is 0.60. The voltage is 12 volts, and the time is 300 seconds. Now, we always check the units on this. The milliliters cancel out, the grams cancel out, the degree C cancels out, the joules cancel out. The volts cancel out here, and the seconds cancel out. The only thing that's left is the amps, and this comes out to 26 amps. The resistance is the voltage divided by the current, or 12 volts, times the units conversion divided by 26 amps, or 0.46 ohms. An automatic coffee maker uses a resistive heating element to boil the 2.4 kilograms of water that's poured into it at 21 degrees C. The current delivered to the coffee pot is 8.5 amps when it is plugged in a 120-volt electrical outlet. If the specific heat capacity of water is 4,186 joules per kilogram degree C, approximately how long does it take to bring the water to boil? Since they did not give us an efficiency, we're going to assume it's 100%. That means what we're determining here is the minimum amount of time that takes the water to boil. If the efficiency is less than 100%, it's going to take longer than this for the water to boil. The correct answer to this is 13 minutes. The energy equals MC delta T, also equals P times T, and also equals I times V times T. So then we can solve this for T. T will equal MC delta T divided by I times V. So the mass is 2.4 kilograms. The specific heat is 4,186 joules per kilogram degree C. The temperature difference is 100 minus 21 degrees C. And then we have to divide by the current, which is 8.5 amps. And the voltage was 120 volts. And this is units conversion. So check your units. This kilogram cancels with that kilogram. This joule cancels with that joule. This degree C cancels with that degree C. This amp cancels with that amp. This volt cancels with that volt. And the seconds is on the bottom twice, so it's 1 over seconds, so it'll come up on top. It's 778 seconds, and that's 13 minutes. Always make sure you check units on things. If you don't, you're going to wind up screwed up. Sylvia wants to change a burned-out bulb in her lamp. When she went to the closet to get a new bulb, she saw that some were labeled 75 watts and others were labeled 100 watts. What is the meaning of these labels? Well, a light bulb, an ordinary light bulb, emits much more heat than it does light. It actually, about 95% of the energy coming out of an ordinary old-fashioned light bulb is come also as infrared, which we call as heat. The other 5% is light. And also this designation is also the power consumed by the bulb. So the correct answer to this is both 2 and 3 are correct. It's the power emitted by the bulb as light and heat, and it's also the power consumed by the bulb. Two incandescent bulbs operate 120 volts. One is marked 75 watts, the other is marked 100 watts. Which bulb has the greatest resistance? It'll be the 75-watt bulb. Power equals V squared over R, so R equals V squared over P. You plug the numbers in. The 75-watt bulb has 192 ohms resistance. The 100-watt bulb has 144 ohm resistance. So definitely the 75. Two heaters are operated at 240 volts. One has 3 times the resistance as the other. The heater with the least resistance will give out the most heat. So the smaller one. Power equals V squared over R, so it's proportional 1 over R. Smaller the R, the greater the power, and the greater the power, the greater the heat. The insulated wiring in a house can safely carry a maximum current of 18 amps. The electrical outlets in the house provide an alternating voltage of 120 volts. A space heater, when plugged into the outlet, operates at an average power of 1500 watts. How many space heaters can safely be plugged into the single electrical outlet and turned on for an extended period of time? Well, the limiting thing here is the 18 amps. So we need to know the current drawn by the space heater. Power equals I times V, so I equals power divided by voltage. 1500 watts divided 120 volts, 12.5 amps. If you try to plug 2 in there, you'd be drawing 25 amps, and that would either start a fire or probably, if you were lucky, it would blow out the fuse or the circuit breaker. A wire is used as a heating element that has a resistance that is fairly independent of its temperature within its operating range. When a current I flows through the wire, the energy delivered by the heater each minute is E. For what amount of current will the energy delivered by the heater each minute be 4E? It is actually 2. So power equals I squared R, and that equals E over T. So E is I squared RT. So E is proportional I squared, and 2 squared is 4. So 2. Thank you.